Section 4.5, use substitution. Well, finally, the time has come when we can work with integrals and do a little bit more with integrals than what we have been practicing. Up to this point, we've taken just, fairly easy polynomials and worked with the integrals of those. We've been able to say, basically using the power rule, up a power, divide by that new power, increase the power by 1, divide by that new power, and then add c if it was an indefinite integral. So we've been able to work with ones that are really fairly nice. Now what we want to do is raise our game and find out how to work with more complicated functions that are not just polynomials. So that is what use substitution will achieve for us. So let's just kind of go back and recall what a composite function looks like. A composite function is built up of, several functions. In this case, I could say that I could have g of x be 2x squared plus 3, and my f of x function be something like x to the 9th power. And then I could say, well, I'm going to build this function y equals 2x squared plus 3 quantity raised to the 9th power by looking at it as a composite of two functions where g of x gets inserted into the f function. So g goes into f, and that would give me that 2x squared plus 3 raised to the 9th. So that's a composite function built of more than one function. To do the derivative of that was chapter 3 or chapter 2 work for us. We learned about the chain rule, and the chain rule says deal with the outer function, bring it down. So I would have the derivative of y prime would be 9 2x squared plus 3, drop it by a power, so we're at the power of 8. That takes care of the outer function. But the inner function, which we just were talking about, letting that be g of x, now we need to do the derivative of the inside, g of x. That would become a 4x plus 0. And then I could simplify this and have 36x times 2x squared plus 3 to the 8th. Excellent. That was, we got pretty good at doing chain rule derivatives. Now what I want to see us do is be able to take this same function but bring it backwards. Let's integrate it. Well, that looks pretty complicated. However, I kind of know where it came from. It came from here, right? It was a composite function. What I need to be looking for on these is that there's a function that if I took the derivative, I have kind of a sketch of that derivative. And what I see on this particular one is that if I took the derivative of 2x squared plus 3, the derivative would be 4x, which brings me down to an x to the first power. I happen to have an x to the first power right there. So there's some tendencies for these that make you aware that you can use substitution. When I see a derivative present of one of the functions that I'm trying to integrate, it's a good candidate for use substitution. So what we're going to try to do is we're going to try to make a complicated function look like a simple function by using u substitution. Why u? Well, u is just the variable that's assigned to this, so we'll let u equal something. That's why it's called u substitution. And we're going to pick u so that its derivative will look like a remaining part. So in this one, I might let u equal that because the derivative of it looks somewhat like 36x in a way. Okay, so that's the general scheme of what we're doing. So let's take this first problem. The integral of 4x times 2x squared plus 3 quantity to the 7th. Now, what I got to do is I need to look. Is this function something that if I took the derivative would give me something similar to that? Yeah, I do indeed think so, because right here, this has a nice derivative. It's 4x, isn't it? And that's exactly what I'm seeing there. So you just want to step back, analyze it for a moment. What we're going to say is we're going to use substitution. And I'm just going to kind of build a little box over here on the left side. Let's let u equal 2x squared plus 3. then I notice that if I take the derivative of each side, the derivative of u would be du, or 1 du, and the derivative of this would be 4x dx. And amazingly, this is a nice one, matches with this right here, doesn't it? I got 4x dx. So there's going to be some substitution involved here. So I'm going to keep track of this information. I want to use that. Over here, I'm going to build. I'm going to rearrange my terms, and I suggest you do this at least for the first couple problems until you really understand where things are happening. So I'm just rearranging. I'm bringing that 4x back to be next to my dx, and you'll see why in a moment. Next up, let's integrate. This 2x plus 3 is really what I'm assigning to be my u. So this will be u raised to the 7th. And now the 4x dx is the same thing as du. Over here, notice we have the same variables. And you must have that in order to keep integrating. So now I'm all in u's, which is great. And now you're looking at this and you're saying, oh, hey, that's a piece of cake. I know how to integrate power rule. U to the 8th divided by 8 plus some constant because we don't have any integrals of or intervals of integration. All right. So this is an integral of u to the 7th. But I wasn't working with u's originally. I was working with x's. So now sub back so that we can get into x's. We want to get x's worked back in, so we're going to sub this back. And u originally started as 2x squared plus 3. It's now divided by 8 plus a constant. I missed my 8 power. I was stepping back and just analyzing it, but I needed that 8. It was u to the 8th, so don't forget to put that 8 power there. Now, we probably wouldn't do this every time, but this would be some function, some original function. I should be able to take the derivative of this and come out with this little f of x. So 8 comes down, remember your power rule, 8 comes down to x squared plus 3 to the 7th, reducing it by power. Chain rule says it would be a 4x plus 0, all divided by this 8. And notice how my 8s are canceling, and I do believe we have an exact match. So this would be f of x because it was f prime. So f prime gives me little f of x, and it matches up perfectly. I know that I have done my work correctly. There's our answer. U substitution. Try another one. So I'll step back from the problem before you even begin and just analyze. I see an x squared, and I see something like 2x cubed minus 4, that grouping. One of those two things probably is my u. Well, if I took the derivative of something cubed, it lowers by a power. It becomes an x squared, doesn't it? And that's right there. So the derivative of this stuff will come out looking much like that x squared. I know what I'm going to set up my u to be. Let's let u equal 2x cubed minus 4. So here's our u sub. Take the derivative of both sides. So du is equal to 6x plus 0 dx. So it's 6x dx. So this is my u right here, isn't it? I've got that. Let's rearrange these terms. So here's my u, 2x cubed minus 4 raised to the 5th. And that would leave x squared dx together. Well, this much I know is u. Do I have the next piece, x squared plus x squared dx. And I just noticed we made a mistake here. Not you, we, me. That should have been 6x squared, shouldn't it? Now, when I compare these, I want this just to be x squared. I've got this 6 tagging along that I really don't want. So, algebra says we can do this. Multiply both sides by 1/6. It clears it over here, and I'm sitting with 1/6 du is equal to x squared dx. That's what I need. I need x squared dx. Perfect. So now let's go into our substitution. This is u raised to the 5th. 2x cubed minus 4 is u. X squared dx is the same as 1/6 du. Since 1/6 is a multiplier, I can pull it out front and get it kind of out of our way when we integrate. Now, integration is pretty simple. 1/6 of u to the 5th integrates into u to the 6th over 6 plus some c value. Simplifying, I have 1/36 u to the 6th plus c. Now I'm ready to sub back. Sub back in our x. And so x's, I have 1/36. And instead of u, let's put in 2x cubed minus 4 raised to the 6th power plus c. And this would be our original function, capital F of x. If you did a little bit of derivative work, you would find that it would come back and match up perfectly. I think I have time for one more, and then I might have to do a new recording. Indefinite integrals, use substitution. Oh, this one's way complicated, isn't it? We got a cube root going on, and I've got 5x underneath the cube root 1 minus x squared. Okay, just stand back a little bit and analyze. If I took the derivative of that, would it be helpful? Well, I do think it would, because this would become negative 2x. Basically, I've got this x to the first power, which is nice because this is an x to the first power. So use substitution is an excellent technique to use on this one. So let's let u equal, there's my u sub. Let's let u equal 1 minus x squared. That means du is equal to negative 2x dx. Okay, for a moment I'm going to go back up to this original problem and just kind of rearrange stuff. The 5 is a multiplier. I could pull that out front. This cube root can be written as 1 minus x squared to the 1/3 power. And then I've got x dx remaining, because remember I took my 5 and moved it forward in front of the integral sign. What I need x dx, don't I? This is almost x dx, it's just I need to get rid of that minus 2 multiplier. So let's divide by negative 2. Same thing as multiplying by negative 1/2. Here I get the 2's to cancel, the negative goes to plus. I've got x dx, which I needed, and negative 1/2 du represents x dx. Okay, so there's our u sub box. Referencing that, I've got 5, integration of. This is my u. So I'm going to have u to the 1/3. Right there's our u, right? 1 minus x squared is u. X dx is negative 1/2 du. Let's pull our negative 1/2 out front, so we have negative 5 over 2 integral of u to the 1/3 du. Integrate now. Now we're down to a nice power rule. U to the 1/3 plus 3/3, because I'm adding 1. That makes 4/3, so I'm going to be dividing by 4/3, plus some C. That means we have negative 5/2. U to the 4/3 divided by 4/3 is like multiplying by 3/4. We're almost done. So I'm going to have negative 15/8. U is 1 minus x squared, substitute back, to the 4/3 power plus that C. Final answer. And I'm at 15 minutes, so I better stop.